Okay, welcome guys. Yeah, so today let's talking about a very small theorem that which you can easily determine whether a sequence is a universe uniform continuous. Sorry, uniform convergence. I'm stupid. Yeah. Okay, so this theorem is interesting that suppose K is compact. So we work in some matrix space. Suppose K is compact. And A is that f is a sequence of continuous function. So Fn is continuous for each n. And B is that Fn converge pointwisely. So pointwisely, okay, to F such that F is continuous. Okay, so remember that in the usual case that continuous for each n will not need to have a continuous. If Fn is universal, uniform convergence to F, then sure that F will be continuous, right? But in general, you will not. Okay, so C, Fn greater or equal to Fn plus 1, right? Is x for all x. Then Fn converge to F uniformly. Okay, so this is the theorem that I managed to prove. Okay, so this theorem is powerful that because in general, just you can easily use this to prove to show that the sequence is uniform, converge uniform. Proof. So let's say Gn to be Fn minus F. And we say that we know that Fn in F is continuous, so Gn is continuous, and I know that Gn converge pointwisely to 0. Okay. So all we need to prove is to show Gn to 0 uniformly. Okay, uniformly convergent to 0. Okay, so put for epsilon greater than 0, I can define a Kn such that which x belongs to K, and such that the Gn of x greater or equal to epsilon. Okay, so remember that this K is closed. Okay. This is because this is inverse of the closed point. So the continuous function is a inverse closed map. Okay, so this is why K is closed. And the K is a subset of K. So K is compact. And by the theorem by the assumption, I know that Gn greater or equal to Gn plus 1. Okay, so this tell me that this tell me what? This tell me that Kn is greater than Kn plus or equal to Kn contains Kn plus 1. Okay, and keep going. Okay, so let's say fix x belongs to K, and I know that Gn is greater than 0. Gn goes to 0, right? So that means x will not belongs to Kn for n sufficiently large. Right, but this is correct for all x. So which tell you that the intersection of all these Kn from 1 to infinity must be 0, must be empty, right? But there's a theorem that we prove in the compact section such that if you have a compact set which is non-empty and close to, and the final intersection should be non-empty. Okay, so that means there exists n such that Kn is 0, right? But what this means that there exists n such that everything is greater or equal to epsilon, independent of x. Okay. So which means that Gn is uniformly convergent to 0. Okay, yeah. So this is the trick, because Kn is 0, right? So that means independent of x. This epsilon is independent of x, right? So for every epsilon, you can find sufficient n. When n is large enough, then whatever x is, this Kn will be empty. Okay, Okay, so this proves that Gn is uniformly convergent to 0. Okay, so let me just write some remark. So the remark says that the compactness is needed. Okay, is needed. Okay, so let's for example, your Fn is 1 over nx plus 1, right? So this obviously this satisfies this. And if you're working on the 0, 1 open interval, then you can see that this guy satisfies this is continuous and converge to 0 monotonely. But this is not uniform continuous. I guess the reason is that if you put Fn to be 1 over n, they become n times 1 over n plus 1. So this is non-zero, okay? Okay, so let's talking about a little bit, just a little bit deviate of what we originally talking, but it's interesting to talking about this. Okay, so given a matrix space S, so given a matrix space X, I identify a LX. So I define L of X to be this this notation. Let's just use this. L of X will denote all the complex value continuous bounded function in domain X. So all the function from X to real to the complex number, such that F is continuous and bounded. Okay, so bounded means that there exists M such that f of X less or equal to M for all X. Okay, so I can define the suprema of F to be the suprema of X belongs to X such that and f of X take absolute value. So this F is well defined, right? Because due to the compactness of F. Okay. Okay, so easy to show that obviously that when this is 0, that means f is 0 for all points, all x belongs to x. Okay, and obviously your h of x is less or equal to f of x plus g of x, right? It's less or equal to f at this. Okay, so that means you can easily get this by just using a triangular inequality and then take the suprema. Okay, so that means this space is what? Is just a matrix, is another matrix space. And you can define a distance to be f minus g. Okay, so I think this is very straightforward. You just follow all the definition, and you can see that this is another matrix space. Okay, so let me just write down another definition that we will use. So Fn converge to F with respect to the metric of this if and only if Fn converge to F uniformly on X. Okay, so this is this is the theorem. Okay, so this theorem is basically the rephrased version of the previous theorem that I think I proved many maybe 2 or 3 videos ago. Okay, so let me just write down. So there is a theorem that I already proved, such that so this theorem says that suppose you have this, and you can define Mn to be a sup of Fn minus F, X belongs to X. Then the theorem says that Fn converges to F uniformly if and only if Mn approaches to 0 as n goes to infinity. Okay. Yeah, so this is just, you can see that these words just reflect as these definitions, this theorem. So Fn converges as respect to the matrix means that this goes to 0 if only if Fn converges to F uniformly. Okay, so exactly the same thing. Yeah, so let's talking about the theorem, which is our final theorem. Okay, so the above metric in L of x is complete. So remember, what is complete in the real analysis means that every cosy sequence converge in it. Okay, so proof. So that's Fn to be a cosy sequence in L of x. Okay, so now means that for any epsilon greater than 0, I can find n such that when n and both greater than n, I get Fn minus f of m. By respect to the such matrix, right? Such matrix is this. Is that an epsilon, right? Okay. So obviously that this prove what? This prove that Fn by the previous theorem, right? This prove that by the theorem that I think I just proved it in the previously that I just proved in the previously that this will implies that Fn converge uniformly. I think maybe two or three videos before that. Okay, so I will post a link below if you haven't seen this proof. I think it's in one of my previous video, so that Fn will converge uniformly. Okay, and also what? Also F is continuous. Okay, so the reason is that Fn is continuous and Fn converge uniformly, right? So F is continuous, and also F is bounded. The reason is that the reason is what? The reason is that if you choose epsilon to be 1, right? Then you can prove that f, so there exists n such that f minus f of n is less than 1, right? Because if you say that Fn converge uniformly, then you can, for each x, you can prove this, right? So f is bounded. So now f is bounded and f is continuous. That means what? That means f should inside will falls into this, right? Falls into this space. F is continuous and bounded. So f is Fn converge f uniformly, and we will have this. And obviously f belongs to this space. Okay, so, and this space is what we should use in the future if you study the more advanced analysis. Yeah, but basically this is the setting. Okay, so next video we can talk about equicontinuous and Arzelà-Ascoli theorem, which is the most powerful theorem in I think it's in uniform convergence. This chapter. See you guys in the next videos.